Hi everybody, welcome to Mathematics 1, Engineering Mathematics. During this short introductory video, I want to give you an outline of what we will cover in this course, how the course is scheduled, and also a little bit about how to prepare for the course. So first things first, my name is Professor Joris van Kersthaber, and you have my email address here on the slide. And during this course, I'll be assisted by 3 teaching assistants, Anju Anish, Mena Marcos, Megan Randi. Each of you, the students, will be assigned to one of 3 groups, and we will publish the assignments during the first or maybe the second week of the course. And there's going to be one TA for each group who will be responsible for answering questions and providing assistance for exercises. This is a year-long course, and the theory lectures will be fully online, so provided via videos such as this one. The exercise sessions are online for now, in light of the evolving COVID-19 situation, and they will continue to be online until at least the 24th of September. If there are any changes in the circumstances, we will let you know from the campus out, and we will post an announcement on Ufora. And speaking of Ufora, we will use Ufora throughout this course for communication. So we'll post announcements, for instance, about the class schedule or about new videos or exercises being uploaded. We'll also provide the class videos via Ufora, as well as the exercises and hints and solutions to the exercises. So if you're not familiar with Ufora, I encourage you to check it out. And in particular, I encourage you to set it up in such a way that the system notifies you with a text message or an email whenever a new piece of content is uploaded. That way, you'll never miss an important announcement. So a little bit about the weekly schedule. So we will post 2 sets of theory videos each week, and each set of videos is approximately 1 hour long. So this is just a little bit shorter than the usual class time would be if we were teaching in person. Class time would be 75 minutes, but the videos will cover roughly the same amount of material. The videos are released on Monday and on Tuesday, and the idea is that you watch the videos, you follow along, and you pause as necessary or rewind whenever you have to, and you take notes and internalize the material. So it's very important not just to passively watch the videos, but to work with the material and to make sure that you understand everything that's being taught along the way, because that is the only way to properly master the material. I should also point out at this point in time that the theory videos are the main source of truth for this course. They're the only source of information about the theory material. There's no written course notes or no book to take recourse to. The videos are the important part. Likewise, for problem sets, we will release problem sets every week by Wednesday morning, usually, depending on schedule. And it's very important that you actively work through those problem sets. So we will give you a few days in which to try your hand at different problems. And I really encourage you to take the necessary amount of time to work on the problems, to fight with them, so to speak, and to really see if you can get to a working solution. You will notice that this is a very problem-driven, a very applied course, and therefore it's really important to get sufficient practice on problem sets. Of course, it can happen once in a while that there's a problem that doesn't make sense, or that you get stuck halfway through. That happens to the best of us. And so what we will do to mitigate that is we will first of all provide some hints for you, so that if you get stuck somewhere or there's a particularly difficult point that you don't quite get right away, you can consult the hints after you've taken sufficient time and sort of get through that difficult stretch. We will also provide some videos, or rather the TAs will do that, with worked out step-by-step solutions for some of the problems, but these will not cover all of the problems. just a few representative problems. Last, we will provide final solutions for the problems that were posted after the weekend. So you have a little bit of time to really struggle with the problem, build up your own solution, and then after the weekend, typically you can compare your solution with the final answer and see if they match, or if not, what exactly went wrong and where. So at the same time, we recognize that there will be plenty of times where you have questions, either about the theory or about the exercises, and both myself and the TAs will be available for feedback and information. So I will provide bi-weekly Q&A sessions during which you can ask specific questions about the theory, and the TAs likewise will provide you with opportunities to ask questions about the problem sets. So this process is going to be mostly email driven. I will post something on Uvora about that, but the idea is basically that you reach out if you have a problem, and then we take it from there. We try to see if we can resolve it by email or a short chat. One very important thing to note, and I will come back to this a couple of times, is when asking questions, please provide context. Show us a little bit of what you're thinking about, what you've already tried, and try to ask specific questions. And this is important for two reasons. One is, if you ask a specific question, then we can give you specific feedback. If you say, I don't understand this trigonometric formula, or I don't understand why there's a minus here and a plus in the solution, that's good. We can look at that together and we can probably solve the problem. If you say, I don't understand trigonometry, then that's much too general for us to be able to help you. So do try to be specific. Secondly, and no less important, is if you get in the habit of providing context and showing your work, then you'll be in a good position to get started on the exam. So we'll come back to this later, but during the exam, you're asked not just to write down the final answer, but also to show the steps that you took in order to get there. So some kind of justification. So if you get in this problem-solving mindset where you work step by step, and specifically you can talk us through the steps, then you'll be in a good position for the exam as well. These are a few examples of what to ask and maybe what not to ask. So once again, if you reach out to us and you can say, well, I'm stuck on this problem, I've tried these 3 things, and I can't continue because this thing went wrong, that's great. We can zoom in right away and help you out. If you say, I don't understand trigonometry, and trigonometry was 3 or 6 months ago, then it's going to be more difficult to help you out. Likewise, if you ask for complete solutions for a problem, that's not so useful, and we will probably not provide them to you. So you'll see that the course is very solution and very problem driven, and trying to figure out what the general line of thought is from collecting solutions is not a good strategy. What is a good strategy is trying all of the problems that we post yourself, working through the solution or building up your own solution, and then asking us if there's something wrong to tell us where it went wrong. So again, making it specific rather than general. And now a little bit about the course content, just to set the record straight. So there are 6 large-scale topics that we'll cover. Each will take about 2-ish weeks. So the first topic that we'll cover starting from this week is trigonometry, and then we'll move on a bit to coordinate geometry. We'll do some limits and continuity, and then we'll do the mainstays of calculus, so differential calculus, a little bit of algebra, and integral calculus. And that will cover semester 1. And specifically for this month, what we are going to look at, once again, is trigonometry. And this week, we'll cover the basic definitions and some of the fundamental trigonometric identities. And then during the second video, we'll cover a lot of formulas that relate different trigonometric functions and identities. You'll see this is quite a formula-heavy video. There's probably around 20 formulas in there. But once you know and understand those formulas, then you can do anything you want with trigonometry. And so then specifically in week 2, what we'll do is we'll look a little bit at problems that involve trigonometry. So problems that have triangles hidden in them, that involve heights and distances, and that also involve a little bit of inverse trigonometric functions. And the reason for starting with this and for looking at triangles is because a lot of problems in the real world, they have some triangle hidden in them somewhere. So for instance, if you stand somewhere at the base of Namsan Tower, and you know the height of the tower, and you know the angle at which you look at the tower, then you can work out how far away you are from the tower. So there's a triangle hidden in that problem that I just mentioned. And in order to work out those different quantities, you have to use some trigonometry. So that's a very simple, straightforward example. We will see more involved examples when we get to week 2. Then we'll move on in week 3 to geometry and limits and continuity. And that will take us all the way to Chuseok at the end of September. So let me move myself a little bit out of the way. So keep in mind that the schedule is subject to change. So especially in these uncertain times with COVID-19, we sometimes have to make amendments to the schedule. If that happens, you will be informed either from the campus directly if it's a big change, or for small changes, let's say if we change the topic for 1 or 2 of the lectures, they will be announced directly. The announcement will be made directly via Q4. So once again, it's important to make sure that you get all the announcements from Q4. Last, just a little bit about examinations and grading. So I know the exam is very far away still. It's probably not on your mind yet. Just want to set the expectations a bit and maybe give you some useful feedback as to how to prepare for the exams. But it's important to keep in mind that there's 2 exams for this course at the end of each semester, semester 1 and semester 2. And each exam counts for 50% of your grade. And the schedule looks as follows. So in December of this year, there'll be a partial exam covering just the material from semester 1. And in June of next year, there's a final exam covering the material from semester 1 and semester 2. And there's an important note here to make. If you do well in December, that is, if you score at least 10 out of 20 for the December exam, then you get an exemption for the material from semester 1. So you don't have to do the material from semester 1 again in June. So I really encourage you to do well, to work hard for the December exam, because if you get that exemption, then you don't have to work as much in June. You can make things easy in June, and you can have a nice, relaxing summer vacation. If you don't make it through the June exam, if you fail the June exam, then there's a reset exam in August. And here it's important to note, if you fail the June exam, you have to retake both material from semester 1 and 2 in August. And last, a little bit about general principles to keep in mind when you study for this course. So it's very important to keep in mind that this is an applied mathematical course. So you will learn how to apply mathematical techniques to solve advanced practical problems. So we're not applied mathematicians, we're definitely not lawyers, we're not interested in mathematics just for the sake of mathematics. We want to use mathematical techniques in our field of study, whether it's biotech, environmental technology, food science, data science, doesn't matter, but we want to apply math. And the exam is structured to test how well you can do that. So it tests how well you can apply what you've learned to new problems. So what does that mean for you? Well, it means that practice really makes perfect. So you should set some time aside in your schedule to work every week on this course, because doing a little bit every week is is much better than leaving it until the end, having a huge cram session and panic and tears at the end. So think a little bit about an Olympic athlete. If you go to the Olympic Games for weightlifting, then you wouldn't sit on the couch for 3 months and then try to do some weightlifting just before you have to go to the Olympic Games. You would work on your game a little bit every week, and you would slowly get stronger little by little. And it's the same thing for mathematics. So if you do a little bit every week, it's much better than bunching it all up at the end. This is also going to be important for the other courses that you take, Math 2, Math 3, and beyond. So be structured and take care of your schedule so that you can work regularly rather than in bursts. Also, again, emphasizing the exam questions will be different from the problem sets. There will not be any questions on the exam that come straight from the problem sets. So don't try to memorize solutions. That is not the right way to go about things. It's perfectly okay if you don't understand a solution that is given, but what you should do in that case is work through the solution by yourself, figure out where exactly it goes wrong, and it is possible that that's the first step in the solution. But once you know where it goes wrong, reach out to me, reach out to the TAs and say, Professor or TA such and such, I'm having problems with this area, can you explain? And we'll be able to help you. And last, get in the habit of showing your work. I already mentioned this helps us give you specific feedback. It's also important for the exam. So if you make a mistake somewhere along the way, and you've shown us your steps, and we can determine that up to this point everything was correct, but then it went off the rails a little bit, that's okay. We will still give you partial credit for what you did right. Conversely, if you just write down the final answer, even if it's right, we will not be able to accept that as given. So you need to provide some justification, some steps as to how you got to your solution. Think a little bit about what you would do if after you graduate you go into industry and your boss gives you a challenging problem to solve. Let's say you work in Samsung Biologics, there's a new process to manufacture vaccines, and your boss tells you, well, work out for me what the rate of change is at which we should feed materials into the machine to produce vaccines at an optimal rate. And you go to your desk, you solve the problem, you use all the mathematics that you've learned here, and you go to your boss and you say, well, we should feed in 10 liters of material per second. And that's all you tell your boss. Your boss would not be very happy if you just gave them one number. They would ask you like, well, okay, that sounds a little bit high or sounds a bit low. What assumptions did you make in order to derive that number? Or what model did you use to get there? Or what approximations did you use to get to that answer? And your boss would also ask you to gently convince him or her by saying, well, okay, I started from this rate of change, and I applied this, and then I used this approximation, and then finally I got to the answer, which is 10 liters per second, or whatever it is. So in the real world too, you will be asked to write reports, to give justifications, to show your work, in other words. So if you get in the habit of doing that early on, then you will ace it at university, and you'll also do well later on. So once again, that's what I encourage you to do. So thank you, that concludes the introduction, and now we'll move on to the actual material, and we'll start with trigonometry. Thank you.